Let's talk about how quickly radioactivity will occur. We talked about how it occurs, right? Too many protons, too many neutrons, the nucleus is left in an excited state, whatever the case may be. We've talked about the details of the reaction a little bit more, like what changes into what, how many protons we got on this side, and whatever, and what nucleus is produced as a result of alpha decay or beta negative or beta positive or whatever the case may be. But we haven't talked about the rate at which it occurs, how quickly it occurs. In order to do that, we have to define a new term called half-life, which some of you may have heard of before. In fact, lots of you in math class, in Math 30, would have done an example of exponential growth and decay involving half-life. So this may be review for some or even all of you. Half-life we're going to define as the time that it takes statistically for 1/2 of a sample to decay. So for instance, if you've got 1 kilogram, it will take a period of time equal to 1 half-life to get down to 0.5 kilograms. If the half-life is 6 years, it takes 6 years to get down to a half-life of whatever, and to get down to a 1/2 kilogram of whatever sample you started with. If your half-life is 24 years, then it takes 24 years to get down to 0.5 kilograms. Statistically. Why do we mention that word statistically in there? Because everything that we're going to do with half-life is based on probability. We don't know when a nucleus is going to decay into another nucleus. It's a natural process. It's a spontaneous process. We don't control it. We don't know when it's going to happen. But we have statistics that can allow us to predict when it's going to happen. And if the sample size is big enough, then those statistics work pretty well. Let me give you an analogy here. We have statistics that say when you flip a coin, it's going to end up tails 50% of the time. If you flip 2 coins, you're going to end up statistically with 1 head and 1 tail. If you flip 4 coins, statistically you're going to end up with 2 heads and 2 tails, right? We can make predictions based on statistics what we're going to see in the end. But because we're dealing with such a small sample size, 1 coin, 2 coins, 4 coins, really, statistics don't always work, right? You could flip 4 coins and quite easily get 4 heads. Statistically, you won't, but it could easily happen. But what if we flip 10,000 coins? If you have a big enough sample size, 10,000 coins, and you flip them all, what are you going to end up with? Well, statistically, 5,000 heads and 5,000 tails. It may vary a little bit. You may end up with 4,964 heads and the rest tails, or vice versa. But it's going to be pretty much 50-50. The bigger the sample size, the closer to 50-50 it's going to be. Our statistics work not very well with small numbers, but they work very, very well with big numbers. That's what we're going to do with radioactivity. Because it's a random process, just like flipping a coin is a random process, we have to base our numbers on statistics. After 1 half-life, you will statistically have, let's say the half-life is 5 years, you will statistically have 0.5 kilograms of that left. You may have 0.49 kilograms or 0.52 kilograms. Okay, we don't know. The bigger the sample size, the closer you're probably going to be to 0.5 kilograms. The best we can do is say, on average, we're going to have 0.5 kilograms left. Now, I'm not trying to simplify it for you guys. I'm not trying to dummy it down for you guys because you guys aren't smart enough to understand what real physics people can understand. Nobody knows. Nobody can make a better prediction than you're going to make in 5 minutes. Nobody can. It's a natural process. It's a spontaneous process. It's a random process, even for brilliant people that have a PhD in physics. They can't predict the flip of a coin any better than you can. And they can't predict how much exactly is going to be left after 5 years any more than you can. They're going to base it on statistics and probability, just as you're going to base it on statistics and probability. All right. Let's give you a couple equations that will describe this. The first one doesn't appear on your data sheet, unfortunately, but that's okay because it's not a very hard one to figure out. Little n stands for the number of half-lives that have gone by. So if the half-life in the last example was 5 years, 20 years have gone by, the number of half-lives would be 20 divided by 5, which is 4 half-lives. If the half-life is 7 years and 35 years have gone by, they would say, well, the total time, 35 years divided by half-life of 7 years gives me 5 half-lives. You're going to take the total time divided by the time for 1 half-life. Does that ring a bell a little bit? Total divided by the amount for 1 gives you a number. Number of half-lives, total time divided by the time for 1 half-life. It's not on our data sheet, unfortunately. The next equation is on your data sheet. N is equal to n sub 0, 1/2 to the little n. And you might recognize that from Math 30. How many people kind of look at that and say, hey, it kind of rings a bell a little bit? N would stand for the final amount, what you end up with after all is said and done. How much you got left? And 0 would stand for the initial amount. It's what you start with. How much you have when the whole process began. And of course, little n is the number of half-lives, not the half-life, but the number of half-lives. A combination of these two equations is going to solve anything you're looking to solve for. Hey, we're missing something. Notice over here, in fact, everywhere in here, we left off units. The half-life could be, what are you going to measure that? Seconds? Sure you could. Seconds, hours, days, years, whatever you want, as long as t is in the same units, right? What about the amount? It could be grams, kilograms, could be just a number. It could be a percent. It could be a becquerel. You never even heard of that before. A becquerel is a unit of radioactivity, a unit of radioactive decay. It's how quickly it's decaying, the number of decays per second. 5 becquerel, 5 decays per second are taking place. Basically, it's an amount. Anything that indicates an amount. The initial amount, doesn't matter what you use as long as it's the same as for n. Grams, kilograms, percent, number, becquerel, and so on. Here are 2 examples that I want to do with you. Here's the first. It says radon-222 has a half-life of 3.82 days. All right, let's write that in this, the half-life. What percent remains after 2 weeks? All right, this is going to be T. I'm going to circle days and weeks. I don't care what units you use. Neither of them are bad, but you got to be in the same unit. So just remember that. Go to days for both of them. Go to weeks for both of them. Doesn't really matter. We're looking for what percent remains. What are we looking for? What variable? Little n, big N sub 0. What is it? Big N. We're looking for the amount that remains. The final amount, we're looking for big N. So what do you want to do here? Let's say big N is equal to n sub 0, 1/2 to the little n. We don't know what little n is, so let's find it. This is the equation that doesn't appear on your data sheet. We're going to say, I'm going to say 14 days divided by 3.82 days. Okay, you could have went weeks. I think it's easier to go days. And when we do this, we get 14 divided by 3.82. Gives me 3.6649. That's how many half-lives have gone by. So now let's plug in, what's N0? Yep, it's 100. And you're looking for the final percent, then what's the initial percent? It's 100. Again, we could use grams, we could use kilograms, we could use becquerel, whatever we want, as long as it indicates an amount. They gave us percent, we'll go with percent. 100 times a half times, or to the exponent, 3.6649. Now, we're going to do this as a group because I don't want you to get mixed up with how you enter this into your calculator. You're going to say 100 times 0.5, not times 10 to the 3.6, but rather this little hat button there, 3.6649. Do that math, 7.88%. After 3.6 half-lives, you got 7.8% left of what you started with. You get a number that's bigger than the original amount, you made a mistake. Because you're never going to end up with more than you started with, right? Have a look at those two questions, please. Just a word of caution. There's a little bit of a typo here. It's not serious, but it is a typo nonetheless. Question number 2 says, how much of a 100 milligram sample will be left? This is N. And we're looking for, this is N0. We're looking for N. The answer they give us is 75%. Milligrams percent. Should be the same units, right? If they gave us milligrams in the question, what should we get in the answer? Milligrams, right? Because we started with 100 milligrams, the number will be the same. It's still going to be 75 as your answer. But if you started with a number that wasn't 100, then the percent would be different than the number of milligrams. So just watch that as you're going through those questions. Let's try one more example. This one's a little bit different. It says, half-life of carbon-14 is 5,730 years. Let's label that as T1 half. Doesn't look much like a half. There we go. That's better. How long does it take 12.5 kilograms of carbon-14 to decay to 400 grams? This is going to be N sub 0, what we start with. This is going to be N. You have trouble distinguishing what's N and what's N0? N is always smaller than N0. N0 is the big number. Okay, N is the smaller number. I'm going to circle kilograms and grams there. I don't care which one you use, grams or kilograms, but you got to be consistent through the question. So we're going to circle that to remind us to be consistent. What are we looking for? We're looking for T. Well, we only have one equation that allows us to find T, and that's the one that doesn't appear on my data sheet. N is equal to T over T1 half. We'll rearrange that. We get N times T1 half. Good. N is, we don't know what it is, do we? We know what T1 half is, but we don't know what the value of N is. So that's not going to work for me, not yet, at least. We've ran into this problem since the beginning of Physics 20, though, right? You try an equation to solve for something, and it doesn't work because you have too many unknowns. So then you try to find another equation that will allow you to solve for that variable and then go back to the first one. Well, the second equation here that we're going to go to is N is equal to N sub 0, 1 half to the little n. It's the only other one we have. How do we rearrange this to solve for a little n? Yeah, we don't like that, do we? Some of you don't like that. I don't like that. You want to solve for a little n? Let's say n over n0 is equal to 1 half to the little n. And then a little n is equal to log n over n0 over log of 1 half. There's good news if you don't like logarithms. There will never be a question that you get on a diploma exam where you have to use logarithms. There'll be questions where you can use logarithms like this one, but there's always another option. I'll explain what that other option is in a minute once we're finished going through this. Bottom line is, you don't like logs, you don't have to use logs. There's another way. All right, let's get little n this way. It's going to be log n over n0. We're going to say 0.4 kilograms over 12.5 kilograms. Let's divide that by log of 0.5. And when we do that math, let's do this on our calculator just to make sure we can get this, okay? Let's say log, got brackets already, 0.4 divided by 12.5. We're going to get a negative number there. Let's divide that by log of 0.5, end the bracket. Gives me positive 4.97. We can plug that in here now. 4.97 times the half-life of 5,730 years. And it's going to work out to be, what, 26,000, 27,000? 28,453, 2.85 times 10 to the 3 years. You may also see that written, by the way, with an A after it instead of a Y. A would stand for annum, years. Same thing. How many people like logarithms? Hands up. How many people despise logarithms? I'll put my hand up for that. I don't like logarithms at all. Never have. There's another way. There's another way if n works out to be a whole number or real close to a whole number. Okay, this wouldn't work if n was 4.31. It works because n is pretty much 5. Okay, but the good news is if you ever have to go through something like this on an exam, n will be a whole number or real close to a whole number. So let's try the other method that I call the divide by 2 method. It includes creating a little table with a little n and big N. Little n stands for the number of half-lives. After 0 half-lives, what do I have left? Well, I started off with 12.5 kilograms. After 0 half-lives, I got 12.5 kilograms. Nothing's happened. After 1 half-life, what do I have left? 6.25 kilograms. After 2 half-lives, 3.125 kilograms. After 3 half-lives, let's divide that by 2. 1.5625. After 4 half-lives, I get half of that. 0.78125. After 5 half-lives, I've got 0.3906 kilograms. Stop right there. That's real close to 0.4 kilograms, right? How many half-lives does it take to get down to 0.4 kilograms? Pretty much 5 half-lives. So what we could do is take this number for the number of half-lives, 5 instead of 4.97. If you multiplied 5 times 5730, you're going to end up with, let's see, 2.87 times 10 to the 3 years. If this is a multiple choice question, they won't both be options. If this is a multiple choice question, you get either one of those and you'll see, oh, okay, I know which one it's supposed to be, right? You'll be able to tell. Even if your number's not exact, you'll be able to tell. If it's a numerical response question, they'll both be keyed correct because they understand. They understand the curriculum specifies that you need to perform simple non-logarithmic half-life calculations, meaning that you might use it sometime if you want, but you never have to use logarithms if you don't want. So because they say that in the program of studies, the curriculum, they'll take this method, even though it doesn't give you the perfect answer. But they're not going to mark it wrong because you've done it a little bit better using logarithms. So either one of those would be correct. I'd be fine with that on a unit test as well. Good? Comfortable there? Here's what I'd like you to do for homework on this. Okay, you've already got worksheet number 24, which lots of you have already finished. But if you haven't finished that up, it should go pretty quickly for you. In addition to worksheet 24, I want you to do worksheet 25, but not the whole thing. Only questions 2, 7, and 11.